Awesome, thank you. Good morning, and thank you very much for taking the time to join us today for the PhD qualifying exam presentation of my PhD advisee, Binesh Kumar. Binesh is a principal senior research engineer at Medtronic and has been with my lab since 2020, working on projects at the intersection of machine learning, biomedical engineering, and health sciences. Today, his presentation will be focused on a recent initiative started in my lab and in collaboration with colleagues at different universities, including University of British Columbia. And it's on precision oncology. We are going to talk about the application of AI, particularly reinforcement learning to theranostics in diagnosing and therapy of cancer. About the format of the presentation today, the presentation itself will be allotted about 15 minutes, after which we'll open the floor to questions from the general audience for 10 minutes. After those 10 minutes, we'll ask everyone except the examination committee to leave the room for a closed door question and answering session. And we'll conclude the session after the closed door meeting. The results of the examination will be formally announced by the committee chair, Dr. Nassar, via email in the coming days. So no immediate decision is expected today. However, a formal decision may be shared if one is made. With that, I would like to ask you to welcome Binesh, and let's get this started.
Thank you so much. Good morning, everyone. Thank you, Dr. Wahid, for the introduction, and thanks to the committee for giving me an opportunity to work on this problem. Today we're going to talk about precision oncology a little bit, to introduce a therapy regimen called Theranostics. Then we are going to look at some of the applications of machine learning or recent study or research in the precision oncology space, primarily focused on machine learning, how machine learning aided some of the precision oncology techniques. We're going to look at the state of the art in decision support systems in Theranostics. And also there is an experiment which sort of demonstrates a toy experiment of how to use machine learning for therapy planning. With that, could I talk about oncology and cancer a little bit, even though we are all aware of what cancer is. Oncology is a branch of medicine that treats cancer. So what is cancer? Cancer is a group of genetic disease which is caused by changes in genes, but changes the way the cell replicates. Why are we talking about cancer? In 2020 alone, there were over 10 million deaths around the world because of cancer. And it's a problem today. And it's not going away. Looking at the projection from Global Cancer Observatory, from World Health Organization, you can see that it's going to be a much bigger problem in 2040. And no one is spared, right? No one region, no one country is spared from whether it's a developed country, non-developed country, everyone has an increased projection for cancer in the next 20 years, by 20 years. So what's the reason for cancer, right? The reason for cancer is being observed as genetic changes, which is genetic changes that makes the replication of cells different than the normal cells. It could be due to a hereditary effect. It could be due to an external damage to the DNA, either through radiation or smoking and so on, right? And there are over 100 plus types of cancer. I'm not kidding when I say that if you go to National Cancer Institute's website and look for the types of cancer, you can find cancer with almost all the alphabet, except for Q, C, Y, and so on. How do we treat this sort of cancer? Right? When you have cancer, when a patient has cancer, there are three options. The therapy regimen falls under three different areas. Either it's medical oncology, whether you're going to use a drug to suppress the effect of the cancer, or a radiation oncology, where you're going to use the X-ray beams to deposit and damage the tumor cells, or it could be a surgical oncology, which requires a medical sort of a surgical intervention. The problem with that is cancer is extremely heterogeneous. It varies from patient A to patient B. Not only the cancer type varies, the genomic profile or the profile of the cancer varies from patient to patient. Because of that, some treatment that works for patient A is not assured to work for patient B. Not only that, the medicines which we use today for oncology, most of them are cytotoxic. It could be harmful for your cells. It could damage, it not only help you, in many cases it doesn't help you, and not only that, it could cause you harm without providing you any benefit. How do we address this problem? How do we tailor the treatment regimen based on your based on the patient profile? That's where precision oncology comes into picture. Precision oncology is a treatment regime where the therapeutic plan or the application is based on individual patient profile. It's been over the last decade or so, right when during Obama administration, they started a program called Project Moonshot and Precision Medicine Initiative, and committed over $1.8 billion to National Cancer Institute to research on this specific area. Look at genomic profile, figure out what works for the patient. And you can see that if you treat the number of FDA approval for this sort of therapy over the years, you can see it uptrend. In 2021 to 2022 alone, there were over 9+ FDA approved drugs in precision oncology category. So now let's zoom in and see some of the precision oncology techniques. This is not exhaustive. There are even more techniques. The first one is targeted drug therapy, where you're going to use a drug that matches the genomic profile of the tumor and just affect the way that cell replicates. Either it could be an angiogenesis inhibitor, which prohibits the blood flow into those tumor cells, allowing preventing it from functioning normally. Or it could be monoclonal antibodies introducing molecules, proteasome inhibitors, and signal transducers. That basically you cut the signal that tells the cell to replicate. Or it could be immunotherapy. Immunotherapy is a type of treatment where your body has a natural response to cancer. Right? Once a patient gets cancer, there is a natural response. The body has immunity to fight against cancerous cells. Immunotherapy is the type of category of treatment where we will provide external inducers or enhancers that will further enhance your ability to fight the tumor, particularly tumor infiltrating lymphocytes. That's a category of lymphocytes in your lymph node that will fight the cancerous cells. There are various types of immunotherapy drugs which you can use. Immune checkpoint inhibitors. It's an interesting thing, right? Like when your body's natural response is being inhibited by the body itself, so that it doesn't cause too much of harm. You can use drugs to sort of temporarily remove those checkpoints so that you have bigger response to cancer. So you have that acceleration. Then there is T-cell cancer therapy, which you can transfer more T of those T cells. You can have, the patient can have immune system modulators and so on. There are a variety of techniques within immunotherapy which are approved today for clinical use. We're gonna, this is another sort of therapy regime called radiation therapy, where you use a medical linear accelerator to directly beam X-ray and deposit energy into the cancerous cells and pretty much destroy the DNA and prevents it from replicating. This has been around for over 70 years. The reason why we are talking about, even though it is not directly connected to precision oncology, we are talking about that because some of the new clinical practices around this fits into precision oncology, where you can, sort of look at the predict the prognosis even before you apply a therapy technique in radiation therapy. That's what his Theranostics is. It's probably a new term for most of you. Theranostics is nothing but the combination of therapeutic and diagnostic. So you can use the same the diagnostic medicines, the drugs which you use, especially the radiopharmaceutical drug, and you can add a ligand that will stick to cancerous cells and kill those cancerous cells. How does it help? It helps to stratify the patients even before the treatment is started. So you can know the predictive response. What will be the response, right? You can use the radiopharmaceutical, which is embedded within the same radioactive isotope for your treatment. So you can see what's going on. You can monitor the progression. You can monitor the tumor response in real time. So you know what you are doing when we apply this sort of technique. And also, predict the efficacy. So the way it works is it uses a pairs of radiopharmaceutical, which you're going to talk about in the next session. Next slide. So this is a typical sort of PET scan workflow. Right? You take a molecule, a chemical molecule, you know the biocompatibility of that molecule, right? And you attach a radioisotope. And then you administer that radioisotope hours before, 30 minutes to an hour before the scan. And during the scan, the radioisotope will create gamma radiations, right? So gamma radiations are received by sensors within the PET scan machine and in multiple planes. And the radioisotope emitting gamma radiations are being reconstructed using an image reconstruction algorithm to provide you a PET image. What is a PET image? A PET image is a representation of metabolic response. So when you look at a PET scan of your body, you will see where the metabolism is, where are the hot points in metabolism, like where the deposition is, where there is radioactive activity, and so on. Why is that important? Because the metabolism of cancer cell is slightly different from normal cells. So that helps you visualize those metabolisms using PET scans. So this is the PET scan workflow, right? So what we do is the change in Theranostics is we use the same radioisotope like gallium chloride, fluorine, radioactive fluorine, and we label that with Theranostics drugs, right? So we have the same isotope. The part of the drug will be used using gamma emission. It's used for imaging, and the other part using alpha and beta emission will help you fight the cure the cancer, not cure the cancer, but kill the tumor. Using this technique, you have higher detectability, quantification, prognostication. You can, working both the drugs in hand, both the sort of isotope in hand. You see what you're doing. You can see the response for each of those, doses. Great idea, right? So you have a visibility into what's going on with every patient. Let's see the clinical effect. So this is a clinical study for roughly 700 patients. And you can see the patients who has used, who were given, the lutetium-177 theranostic drug, and standard care had 8.7 months of progression-free survival, where the other one is 3.4. Very good. So now we have clinical evidence. And there are many clinical studies in the last decade around, for clinical drugs for neuroendocrine cancers, thyroid cancers, and prostate cancers. So how's the enthusiasm around the medical community? If you use PubMed as the database for Theranostics for our research, if you search for Theranostic over the years, you can see roughly 30% increase in number of research articles published in PubMed with just Theranostics in it. So we have a drug. We know the effects of the drug. We know it is clinically beneficial for the patient. We know there is interest in the community. Now, you may ask, what's the magic? What's the catch here, right? So this is a study from a multi-center clinical trial where the same level of drugs were given to multiple patients. You could see the response using your PBPK models, if you're going to talk about. But what this will tell you is all the red dots here are patients who did not survive. It's a survival plot. So you could, all the blue ones are patients who survive. So there is a gap in the amount of drug they received, and that affected their overall survival. You could have given them, their oncologists could have given them more drug and increase their decision-tree progression just by managing a good dosimetry. So 23 gray is the measure of energy deposited. So even with 23 gray, you do not have much kidney damage. You could have stretched that treatment a little bit more and improve the quality life or even perhaps the life of the patient. So there is still gap in the way the clinical workflow is built around this. So yeah, there is still scope of improvement, right? Like the dosimetry is sort of the key. Now, now we know dosimetry is the key, and why not everyone is doing performing dosimetry on this sort of therapy. So this is actually a script from the FDA Theranostic Consensus Conference in 2018, where they had researchers from major clinical research facilities as well as representatives of NCI, National Cancer Institute, FDA, and so on. So they were there to debate about how to have a better therapy plan for Theranostics. Everyone agreed that dosimetry is the way to go. You have to control the way the drugs are being delivered, and it should be customized. Where they couldn't agree was the amount of cost, like the cost involved in building individual therapy profiles. That was way too high. And there was tension between the commercial companies who are spending billions of dollars in developing these drugs. And if you add dosimetry as an indication in their regulatory submission, it's going to delay the use of the drug. So they did not get much commercialized interest from the commercial area. And the logistics is way too difficult. Those were some of the voice of customers from the group. So let's summarize it, right? There is shortage of multidisciplinary expertise in oncology. So if you have to do dosimetry for Theranostics, things involves radiology, oncology, and maybe other practices within the hospital. It requires more amount of effort, and many hospitals across the United States do not have that sort of multidisciplinary expertise. And the lack of enough software tools or decision support tools is really impacting the adoption of this dosimetry. Whereas with that, we could further sort of improve the make this treatment available to not everyone just in the United States, but across the world. Having a validated therapy planning tool using for dosimetry for Theranostics is going to have that clinical impact available for everyone in the world. So what's our proposed solution? Our proposed solution is is to use, I mean, if you think about cancer therapy, it's a sequential decision-making process. It involves constantly checking with the patient on what's going on, running tests, feeling the pulse, and making sure that you make the actions that's gonna give you maximum reward, that's quality of life, or prolonged life, or a healthy status. This could be potentially be framed into a reinforcement learning problem, where we could train an agent that can observe the current state of the patient, make therapy decisions, evaluate the actions available from that specific state, and look at the reward it's going to obtain for each of the actions and pick the next best action based on the current state. So that's our sort of a solution framework for dosimetry. Use all the data repositories, use all our expertise, use the in silico experiments, come up with, train an algorithm that can sort of work in a reward hypothesis through which you can select an action at any point in the care plan. There's some details about some of the techniques which we were looking at. Q-learning, obviously. Then I'm going to skip through it for the essence of time. So these are some of the techniques which we were trying to experiment as a solution framework for using RL as a potential decision-making tool for precision oncology. Now let's skip to and see what are some of the machine learning applications. Sorry, I have a couple of planes which I missed to hide. But if you think of the entire therapy plan for precision oncology, like treatment and addressing of care plan for a patient, it's a pyramid. What at the bottom of the pyramid? Having good drugs, right? You need to have good drugs available, good discovery of materials that can create either a good immunoresponse or a good targeted drug therapy or good tumor response. On top of that, we need to have a good diagnostics tools available, right? We need to be able to diagnose and grade the patient health condition and categorize to, either through imaging, digital pathology, or even next generation sequencing to figure out what's the profile for each of the patients. And on top of that, the top of the pyramid is therapy. You need to have, once you diagnose what's the profile, we need to match and find the right drug. It could be because of the nature of where we are operating, we cannot do trial and error methods. So we need to have simulation models that can sort of help you guide the decision on what's the best course of action even before you take it and try it. So either simulation, decision control tools, and so on. If you zoom in a little bit and look at drug discovery, it's a very complicated process, right? When you hear about how long it takes to develop a drug and you hear about timelines around 7 to 8 years, it's a very complicated process. Typical time frame for developing a drug in precision oncology space is 10 to 15 years. And the median cost of drug development is somewhere around $780 million. It's a huge effort. And what they are doing, this is a sort of the workflow for drug development. You start with gene disease identification, find out what compound will give you the best response. And for this, there are tool sets available. There are databases like ChemLib, which has chemical properties of each of the identified drugs. We can comb through, find out the right drug, and then figure out which biomarker indicates your decision condition so that you can select one from ChemLib and simulate and use it. Then the clinical development is the most complicated part, which involves, in many cases, clinical trials. In almost all the cases for drugs, there's clinical trial. Unless you get a de novo, you can skip through a pathway if you are solving a problem which would never existed or solution never existed before. So there are like so this is sort of the complicated workflow, right? We have the opportunity to, and which is being demonstrated by several studies, of how machine learning can sort of accelerate this entire workflow, how we can model, simulate, mine through larger repositories, find out patterns, use that sort of empirical knowledge, which is machine learning is good at, like through patterns, and figure out what's best for the patient and shrink this overall workflow, not in terms of steps, but in terms of timeline. These are a summary of technical areas or studies where machine learning was used recently in the last 4 years. It was used to develop a new chemical compound for colon cancer. A quantitative structure AI model was used to predict inhibitory response. There is RL-based approaches demonstrated using a program called Release that sort of, instead of doing a brute force search through the cumulative library, you can use RL-based algorithm to figure out what works for you better. This is an existing study out there. Then AlphaFold, everyone knows about AlphaFold, the protein structure prediction. Then, DNA sequencing, which is very recent. So there are several, sort of individual pockets of research which has promising aspect in drug discovery. So now, if you look at diagnostics, if you remember the second layer in our pillar, this is sort of a state of the art, even though this is not the state of the art in many healthcare systems. But what you really want to do is screen as many as people you can, right? Statistically, it's been proven that even with breast cancer, we were able to reduce the number of breast cancer mortality by 11% since 1988, primarily because of the amount of screening. The goal is not done yet, but we have made progress where we have statistical evidence that shows that increased screening could result in reduced mortality. How would you make this available for everyone, right? We are looking at 40 million deaths by 2040. How do we sort of look at where machine learning can help? Machine learning can, in the past decade or so, there are a lot of computer-aided diagnostics that really scales up, the task of diagnosing for a specific condition. If you look at the overall workflow, that's not where when it starts. In future, or in some cases in state of the art, you can comb through the data in wearables, Apple Watch, Fitbit, then your primary care provider health note. There are several companies who are operating in this space. One is Nuance, owned by Microsoft, and then your electronic health records. These are all potential areas where you can search for information that will help you identify the risk for a particular disease condition. We want to filter that in level 1, right? Then what you want to do, once your patient is categorized with higher risk, we can send it to diagnose, right? I mean, you can see whether there is an occurrence of a cancer through screening, through diagnosis techniques. Could be either if there is high risk, if there are, if there is a disease or if it's a condition, then you can sort of get into the next workflow step, which is diagnosis, use biopsy, pathology, histology, omics, like genomics, radiomics, for automated diagnosis and grading. At that point, you are grading your disease condition into one of those grades. And then, radiology tumor board, which is the, in many hospitals, you have a tumor board, which involves a list of top surgeons, oncologists, radiologists, who meets and agrees on the care plan. It's sort of manual, which has proven to be effective. So those sort of things where we can have automated, we can take that knowledge, take that human knowledge around diagnosis, and we can automate it so that we can address that, the increasing population who is projected to get affected by this. Some of the studies which we went through, and again, this is the sort of literature survey on where precision oncology, where machine learning was used to accelerate or help diagnose. And it's in the diagnostic space, you see that sort of reflection in the FDA approved devices. So over the time, you can see the number of algorithms, it's in rise. 97 per year, FDA approved. I mean, this is a list published by FDA where there is an algorithm being used for diagnostic purpose. So you can see that sort of reflection in the FDA approved devices. So that means the research is making its way into clinic in diagnostics. Now, from a therapy standpoint, this is where things get a little bit more involved, right? Like here, the actual therapy plan is very sort of interactive. The care provider interacts with the patient, use visual cues, use diagnostic techniques, hear what patient has to say, and sort of look at existing knowledge bases and figure out a therapy plan. So again, it's a longitudinal decision-making process. Sometimes you have full observability where you can see what's going on with the patient, or you have only sensor data when the patient visits you. So the general framework around that is, use of, again, sort of a reward system, right? Like where you have patient state, slide red, which is slightly unhealthy patient. And we have more options, right? The research in this space has created more therapy options. So you sort of look at your experience, your peer experience, your tumor board, and figure out where the prognosis for each of the actions. It could be patient could be healthy, patient could get slightly less healthy or become worse. If you can have a sense of what each action can do, and then establish a reward, you can pretty much train an algorithm to do this. What makes things complicated is, again, noisy data. We're going to talk about the challenges around data and censoring, time between observations and so on. Sorry for the size of the table. These are some of the research studies where an algorithm was used to develop a therapy plan, especially in reinforcement learning. You can see there are enough interest, right? There's never enough interest, but there is sufficiently large number of research papers in this space. But that's reflective of what's in the PubMed. But where we are lacking is clinical trial, right? It stops here. The research stops here, and we are not seeing that level of clinical trials where reinforcement learning or machine learning is used. There are now an n number of challenges which we are going to talk about. So the research community is actively interested, but the clinical trials, if you see the status of the clinical trials, very few are recruiting. In 2022, only 9 of them were recruiting people for the clinical trials. So yeah, the only interventional system that received regulatory approval is the Philips Medical Charge Particle Radiation Therapy System for head and neck cancers. This was one of the, as per FDA records, this is one of the algorithms which were approved for therapy planning. When I looked at the submission document for this, the machine learning was not actually used to make decisions for the developer therapy plan. It was more on the using a convolutional neural network to classify the images better. But the device is overall indicated for therapy planning. So what does it take to solve this problem? So it's a 3-step process, right? You have patient identification. You have to figure out which patient will have the good response for your drug. Then you have to figure out what sort of drug schedule should be maintained. And you should have a long-term sort of health management, right? Many of these drugs do not have immediate response, so you will not immediately see the effects of the drug. So the current dosimetry practices, this is as per the FDA and CDC, not CDC, FDA and NIH. There are flat doses, weight-based dosing, organ-based dosing. So these are pretty, very rudimentary in the sense, you check the weight of the patient and you select a radiation drug profile that works for them better, or flat doses or baseline. An actual data-driven sort of workflow would be to use physiology-based pharmacokinetic models. So these are drug models which are used extensively in drug research, drug response research. So pharmacokinetic model will talk about how your body responds to drug, how the drug is being distributed in your body, and pharmacodynamics will talk about how your body reacts to drug. At the end of the day, for Theranostics, what we are interested in is to figure out biologically effective dose, to make sure that we get the right amount of biologically effective dose to the tumor, and while reducing the biologically effective dose for organs at risk. So we don't want to affect the kidneys, the high-risk organs. So this is an example of a pharmacokinetic model. It's a, if you see, it's a plumbing of the human body, right? Like this is how the drugs flow through your body, through the plasma in your blood. So this is a mathematical sort of representation, highly abstracted mathematical response, mathematical model that shows how the absorption, distribution, metabolism, and excretion of the drug. The current practice is PK models are widely accepted by regulatory bodies to show how the drug will be distributed, which is quite in favor for Theranostics because you can use this for your regulatory submissions. But current practice is, PBK models are built of, linear, like a differential equation for each of the organs, and you will know how much deposition you will get through simulation. A data-driven approach would be, take the population's PBK model, right? Everyone's PBK model of the general population. Then we can, do parameter estimation to figure out how is it tuned to a specific use case for a specific population, for a specific drug. Then you have a PBK model. It could be Dr. Ahira and I, we were probably looking at, we are looking at some of the options to model this problem outside first order ordinary differential equations, either using language models and so on, to sort of figure out the best way to represent the model. The model will tell you, PBK model will tell you what's the drug distribution. Then you use a generic tumor model, a combination of that to predict the response of the, of the tumor and OIR. So, so take the generic model, customize it, then build a generic tumor model, build a pipeline, and see how each drug responds to, how each tumor responds to the drug. And we went through this before, so it's, a personal treatment plan incorporating that data-driven model. We can predict the response. Now you have a reward. Then you can train an agent that can, penalize or reward based on your predicted response and adjust the actions. The gold standard today is some of this is being done today using Monte Carlo simulations, but the lack of expertise within local hospital systems and the amount of time it takes to run a all-body MC simulation is so huge. And there are some open source tools that can help model that. Our thought process is use reinforcement learning, and then since we are using a data created in a simulated environment, there will be inherent errors. So use sim-to-real framework which is quite popular in robotics, to take the model and tune it for real world using data from clinical studies. What are some of the challenges? I mean, obviously, we all know the challenges of data in the healthcare. Data is siloed. Every hospital has their own EHR system, their own PAC system, which doesn't talk to each other. There is a lot of work being done in this space. There is funding for faster transfer of health records between systems, but the consolidation of data for researchers is not there. I mean, there is no one common database where you can go, and there are databases, but not one single large database where it can be used for training. Then data is multiple modality, right? If you look at the diagnostic instruments, testing instruments, biometric instruments, everything used within the hospital system outputs data in different formats. I mean, when I say different formats, some of them are time series, some of them, in different scales. Dealing with that sort of multi-modality and having healthcare device companies to develop systems that can talk to each other and obviously trustworthiness. A lot of algorithms, especially the sepsis prediction algorithm, which was launched by uptake, did not quite get the approval of the clinicians because they were not trusting the algorithm. And the algorithm, when Epic rolled it out, they were not, what do you say? They were not, they did not release data. They did not release data framework around how these decisions are being made. And as soon as it was launched, it got wide. There are a couple of research papers that talks about why the algorithm failed. So, taking the, taking clinicians' confidence. I mean, the actual practitioner's confidence is at most healthy, at most important. Then, the stationary data within shifting population. Right? Just to give a simple example, right? Like if you look at the BMI, the overall distribution increased over the time. That is just the BMI. Think about all the other metabolic readings which you get. So when you train a model, that should be, and obviously adversarial actions, which is one of the focus of the lab, where when you have mission critical systems making decisions for you, how do we keep that secure from people who want to do malicious activity around it? Performance metrics. This is, there is a lot of performance metrics around machine learning algorithms. But one thing which particularly, in parallel or in quite common in the medical field is sensitivity and specificity. So any algorithm which we develop should be, used, should have these considerations to talk the same language as the clinicians. Performance criteria, when we develop an algorithm, should have good sampling efficiency. It should handle the delay in observation. Then the amount of high modality means high dimensions could potentially lead to, higher actions and state spaces. Explainability is a problem. Dispersion, measure of risk, those are like reliability related, criteria. Data requirements, if you have to develop an algorithm, we need both imaging data. Some of them are publicly available. University of Michigan has a repository of 27 or 30 patients with full metadata and imaging, right? Everything which is required. But the challenges, there is a challenge which was opened by American Society of Physicists today or yesterday. Their data is purely in silico, so meaning computer generated data. So that's treated as okay. That's like acceptable to work with an in silico. But in an ideal case, you need absorb those histogram qualitative features from the scan. There are libraries, like open PBPK model library for several drugs. Some of the available data sets, some of them are open, some of them are closed. From a regulatory standpoint, right? A few years ago, FDA released their action plan on how do you validate a software device with machine learning in it. So their action plan was based on 5 different things, right? The first one, you need to have a predetermined change plan. You need to know what your algorithm is going to do out in the field. When you release software as a medical device, you are often controlled at the source. You know your software, you test it, release it. But machine learning algorithms tend to, majority of them, to get the value, you need to have a decision space which is quite large. So you need to have a predetermined change plan for that. Then good machine learning practices. FDA released a guideline of 10 different principles that should go into, making a overall design of machine learning models. Then patient-centric transparency. You need to tell not only the clinicians what the algorithm does, what data is being used. You should also inform the patients who are at most the providers of the data on how the algorithms work. Then bias and robustness. When you train an algorithm, make sure that this is a validation requirement today, where you have to, for the intended use case, you have to show if it has to be operated in the United States, it should reflect your data, on which the algorithm is being tested, should have a reflection of what the actual population of where the device is being used. And of course, once you deploy the software, you have to closely monitor the real world performance. So this is sort of the foundational, pillar of their action plan. And they went a step ahead and released a guiding principle for developing machine learning algorithms. And it was, it was released in collaboration with Health Canada, US FDA, and UK MHRA, their regional healthcare organization, regulatory body. So they have 10 principles, but if you look at the first one, it's total product life cycle. You need to maintain the life cycle of your entire machine learning algorithm, monitor it, look for risks, changes, have the change plan in place, and also focus on human AI team. So they want humans who are using these tools to have a good understanding of how that interaction works, right? Primarily around liability around decision making and so on, right? Then use cases, users are provided clear instructions, monitoring selected data, training data. They said training data assets are independent of training testing sets. There were occurrences where submission had same data set used for both use cases. For IRB, this is purely, the framework is being released. There is a checklist on IRB requirements, but it's at the end of the day, it's the ownership of this is within the institution where the research is being done. For our research, we will be using human data. If I go through the workflow, which is an extraction of IRB review worksheet from University of Washington. This is where we will end up. We most likely in our research framework will be using publicly available data sets. So hence, we will be exempt, fall into the category of exempt research. Now talking about the experiment to see, to take an example from one of the researchers out there, and we try to implement it, right? So, this is one of the studies from University of Texas, Artificial Intelligence and Automation Lab. They built a treatment planning system using deep reinforcement learning. And primarily, they were trying to develop a treatment planning model using reinforcement learning for prostate cancer radiation therapy. Unfortunately, the test, the data, they did not publicize it. They had a hospital committing their data for the study to baseline. They used in silico for the algorithm development, and then they used the actual patient data as a baseline to compare against. But unfortunately, the data is not available. I reached out to the author. So we had to come up with an alternate to replicate this using a simulator. So what the simulator does is, we wanted to figure out what's the optimized radiation profile for a cancer, right? So what I did for this study is use a cell simulator from one of the existing studies out there, where you have a in silico simulator that can go through the cell cycle. Naturally, a cell cycle is, this is a cell cycle. The cell starts at G1, it transfers that into, the cell will go from a G1 state to a S state, which is DNA synthesis. From there, it gets preparation for, splitting, right? Mitosis, so it's split into multiple cells. So the entire logic is built into the simulator. So the simulator is actually a grid of tissue, and each of that cell will go through this tissue cycle. And the tissue cycle is dependent on the amount of sugar you get and the amount of dioxygen. Since the simulator did not replicate the PBK sort of model, it randomly assigned a distribution of sugar and dioxygen so that you have enough to, two different placements. For the radiation, it used a, we want to make sure that you provide the radiation at the center of the cell, which is cancerous. So found the center of the cell from the simulator, then provide the maximum intensity radiation within that radius itself. So in that way, you don't impact the healthy cells. Obviously, the survival probability of the cell, which is built into the simulator, is factored on radiosensitivity factor, right? So that works to our advantage because the cells which are cancerous has lower survivability to radiation than the regular healthy cells. So this is all built into the simulator. So this is sort of the image of that cell area. It's a 50 by 50 cell, and at the beginning of the simulation, a cancer cell is placed at the center of the grid, and let the simulator run. The simulator will replicate the healthy cell as well as the cancerous cell over the time. So indicated by the color. If there is a -1, then it's a cancer cell. If it's 1, there only helps a healthy cells. If it's 0, then there is nothing in there. The tissue area did not grow enough. Which is again like an in silico rudimentary experiment, right? I mean, it doesn't consider the actual flow. It doesn't consider actual PBPK model, even the PK model. The action space tried both DQN and DDN and had a baseline. So, the radiation is measured in gray. It's the amount of energy deposited, right? So we wanted to control for the DQN, there were like 9 possible states, 0 to 4 gray. Sorry, there's a typo with a 0.5 gray interval. And for DDPJ, we had a continuous space of radiation profile between 1 to 5. So the algorithm can decide between 0 to 5 in various steps. And there is a terminal condition. You don't want to, sorry. Don't want to run it forever. So there is obviously terminal condition, either, the tumor, you were able to successfully kill the tumor, or, the tumor has outgrown the healthy cells in that 50-50 area, or 120 to 1200 hours of treatment. The rewards were based on not only just on the number of cancer cells killed, but also the dose, right? I mean, we have a multi-objective criteria, right? Even in Theranostics, we want to kill the maximum number of cancerous cells, but reduce the number of collateral damage. So the reward system built was, around that. And if the cancer takes over the whole grid, then, the reward is -1. During the training, the agent was trained for 100 episodes with 300 time steps, and using 3D algorithm for, it did not convert, but the results of this were quite similar to the original paper. Because of the noise, I tried changing the reward function, to have a better, stable convergence. So this is how the baseline. So the baseline is give 2 gray of energy for as long as 1200 hours, right? And if you see the baseline, after 816 hours of radiation, there were no cancerous cells. There are some black cells, which are like they killed cells which are not active. And depending on the algorithm, the simulator, it grows back the healthy cells. You can see the DQN worked better. It was able to kill the cancer cell in 192 hours with lesser amount of grays. Where the DDPG algorithm used 104, 408. So this is sort of the time step progression of how the simulator responded. For at the beginning, you have a simulator ran for 350 hours and created a cancer blob at the center of the image. And here is the radiation profile which the algorithm came up with. Obviously, so this is the baseline dosing 2 gray for infinity, like 1200 hours. DQN dosing, it was started with high, it adjusted the dose and then stayed there. Then if you look at DDPG, it controlled, it delivered at 1, but the interval for dosing, it reduced the fraction time. So it gave more doses. So this is sort of the baseline comparison. If the tumor control probability is roughly 100%. Healthy cell scale. Those are the metrics which typically they used in clinical practice for checking the effectivity. The reason why I think it did not converge is because of the reward system. Initially the way the simulator was set up was, it was trying to send the lowest dose because you have two objectives. It was trying to stay within, get the short-term incentive of delivering that short-term lower number of doses, and introduce a new goal. Like if at the end of the episode, if it cannot kill the cancer, then a -1 reward system introduced, so that even then, I think the discounting factor is making a play here. So that's, it could be improved. There are, the simulator could be improved in terms of reflecting the actual dynamics of the body, as well as, introducing additional sort of factors, especially around rewards. So now we are at the sort of end of the presentation. These are some of the questions which we are trying to answer with our engagement around this. This is particularly interesting for me because I have a personal motivation. I lost someone very near to me because of cancer, not because of the cancer, but because of the amount of dosing, and the body was not strong enough to withstand, the treatment. So, we're gonna, use our brain, use our skills and everything in our power to address this problem, right, through these questions. I think that's that's it. Thank you for staying with me. I know it's a really long presentation.
Oh, thank you. Great work. Now we have a few minutes for questions from the general audience. If you have any questions about the presentation, whether you are in the committee or not, please feel free to ask now.
Hey, Binesh, that was great. I wanted to ask, do you have an idea of where you can get proper or more reflective reward functions of the kind of treatment you would desire to come out of these algorithms? Because for sure, when I'm using that reward function, to me, right, the behaviors of the reward function is what exhibits the behaviors during training. And so that excessive negative reward in proportion to the immediate reward throughout training, you mean like in some settings, sparse rewards are more representative of what outcomes you want, but it makes it harder to control what kind of behaviors occur during training.
Right. I mean, that's the second.
This is a question or a PhD thesis?
That's actually one of the challenges, right? Having a good sense of state so that you can come up with a better reward function. Having a better model. In fact, our research partners in University of British Columbia, what they're proposing is sort of going out with a full-blown digital twin of the human itself, able to model an entire system so that it's quite reflective or quite matches what's in the actual world. That's the goal, right? So now you have a good control of the state. Now you have a good control of your transition. You feel from the environment that what I mean, we have enough expertise in terms of responses, how body responses to external factors, to drugs. Those are being documented. I feel like there are enough knowledge bases out there. It's just that we have to come up with a coherent, holistic approach to model that so that we can have a better reward system. In this case, I couldn't find, the training was like 16 hours. The simulator was way too long, so it didn't give me a lot of time to try out something which is, much more realistic.
So inside your RL model, right? I see there were two more models over there. One was GPK model and the other. So how are you going to develop those models? Like, what's the plan for that?
I don't know whether we will be developing those, but during the research, what we found is majority of the researchers are using either a DQN based model for this sort of use cases. Almost every paper, right, around therapy planning, care provided, or around TQN. So we may have to experiment, like compare those models against our performance metric, not just how well it performs, but how well it understands, how well it can explain how it performs, and also meet the regulatory requirements, right? I mean, some things which are needed to get into the clinic.
I think Vivek's question was more about how are you going to create a simulator that is
Oh.
the agent?
Oh, sorry. So, I mean, for simulator, for PBBK, for the drug response, for several compounds are publicly available. That's becoming a more and more regulatory requirement to have that model published for use. So when you submit your paper for either 510K sort of framework, you have to submit that PBBK model. And the research community, especially Pfizer and Novartis, who are big into this space, they contribute to this open community where you have these models in place. Then drug response is relatively a simpler problem than the PBBK problem, because we know how the cells replicate and how cells behave for external actions. It's a plumbing that's complex than the actual reaction of the end where the plumbing brings the run to.
One more.
Yeah, sure.
So there is a very limited data, right, already. And now you're thinking of trying to produce synthetic data out of it, right? So do you think that that heterogeneity and the generalization will be lost because of those synthetic data?
Obviously, we have to get into more standardized data collection, right? The knowledge bases like Genome Atlas, that's a repository in their cancer genomes, where if you can eliminate some of the interpretation involved by humans, like in genome, you can run next generation sequencing on the lab itself and then, load that data. And especially Theranostics is a solution for that. I mean, because you can see how the drug moves around the body, you have a much more clearer representation. Right? You can see what's going on. Now you have to figure out a common standard on how to measure it. So measuring from the institution A to institution B should be standardized. There is actually a protocol on how, but protocols are protocols, right? Like it doesn't fit into the clinical workflow. People are doing it, they do it. So the study from University of Michigan, they have a standard data set. So I mean, we learn what sort of noise we can expect, and eventually model the noise itself, somehow.
Because you're going to do a very challenging work of training out of model.
Right. Yeah, that's exactly why clinical study, that you see the difference between clinical study and researchers.
I'd like to follow up question on the models. So, I'm just very curious. My background is mechanical engineering. So when we talk about models, we always follow certain kind of physical governing laws. Like the simplest will be like Newton laws, right? So when you talk about your models, and then what is the governing laws behind those models? Do you follow any of this?
So PBBK model is actually a mathematical model of how the drug flows into your body. So it's being measured. So what they do is they inject trackers, and you see how much deposition. The blood has plasma piece, which is volatile, moves around the body, right? So you know where it's gonna get absorbed, where it's gonna get metabolized, where it's gonna get distributed. So PBK is like bringing that physiology knowledge into your pharmacokinetic model.
Your physiology knowledge is kind of physical principle you follow, right, when you develop.
Like flow rate. Flow rate is, the pressure flow rate is actually built into the model. So
you mentioned a lot of models, so I get confused. So what is the principle behind that? So then like you have this
pharmacology based
model,
yeah.
And you mentioned you use the ordinary differential equation.
That's
those are mathematical language. So I'm interested in the principles behind that.
Sure. Actually, the first order equations, ordinary differential equations for that is available, like especially for the Lutetium 177, which is used in prostate cancer, is actually available, published. So you can get the actual equations.
Yeah,
Yeah.
I'm not interested
But-
in
but the
equation. I'm interested
Interpretation,
in the critical principle
sure,
behind those equations.
right. I don't know about how those models were. It's an abstraction for sure. If someone actually spent time in measuring this and come up with an abstraction, but I don't know whether it flows. Probably follows the flow rate mechanisms, your blood pressure, but
So that comes back to the big question. So when you do your models, your whole purpose is to find those models so that you can precisely predict what happens, right?
right.
So your model, are you just going to base on the data you have, or you have to actually dig deeper into why they are making sense behind that?
We have to. I mean, the PBPK models which are published are sort of accepted as the
I
standard.
know, yeah,
So,
it's in the publication.
it's-
So.
Do we try to make it better and better in terms of what, right? Like we have to come up with sort of metrics on how it, the pitfalls of the existing published models and try to optimize it. We are much more interested in sort of personalizing it. How does everything which you can sense or measure from a patient, how does that factor or customize an existing model? That's where we are sort of focused by repurposing what's already in there. Like use the existing PBK model, see how much we can customize and what factors playing. Yeah, that's the open research question.
A quick note on that, the first order differential equations, ordinary differential equations are super abstracted. As in, there's somebody probably with a mechanical engineering background who wanted to create the simplest possible differential equation describing changes in the state of the cell. And the only parameters that need to be fine-tuned are a couple of coefficients. Those models are not accurate, no model is, but these models are super simplified for the purposes of providing a ground truth. Part of what Binesh will be working on later on is to extend these models instead of relying on first order differential equations or even relying on models of fluid dynamics, but with a completely data-driven model and see whether that would work. But this is a longer discussion. While we are at the time for general Q&A, I was wondering if there is anyone else who would like to pose a quick question.
Sure. We have to learn how to connect it. Congratulations, Binesh, because this is such a great topic, and I'm happy to see that our students, our university and our faculty are invested on this. But my question is, what is your next goal in the research? What do you want to do? What do you want to achieve?
This is a problem which we are at our lab cannot solve by ourselves. So we are looking at our partners at UBC who is sort of world's second largest or second leading investigators in Theranostics and use their expertise to especially around biological, chemical, physical response of drugs. And they have a hospital system which is much more easier to operate to get access to some of the data, some of the observations, and really narrow down our scope of research to addressing. So our focus is coming up with a good dynamic treatment plan, a tool that can be used by anyone who has access to it. Right? That's our overarching goal. So for that, there are a lot of questions around healthcare system that should be addressed. Standardization, hospital. PET scan is sort of standard. It has more adoption than CT, especially because of the number of patients who are getting prostate cancer. So there are, work with our partners, use their expertise, bring in our reinforcement learning, machine learning expertise, combine voices, and try out a few of these models in silico environment.
Thank you. Thank you. Congratulations.
Thank you very much, Binesh. Thank you everyone for joining us. Let's give another round of applause to Binesh. Now, I would like to ask everyone except Binesh and the examination committee to leave the room for the closed door question and answer. And Binesh, can you stop the recording, please? Thank you.
It's not running.
This is too late.
If you find it.
Congratulations.
Thank you so
See
much.
you. Bye.
Thank you.